All right, so our next speaker will be Aldo, who's going to be talking about halos of star forming in quiescent galaxies.
Okay, can you hear me? Okay, good. Is there a pointer here? Okay. Okay, thank you. Okay, great. So, thanks for the opportunity to give me this talk. Actually, I will describe the work by two students, wonderful students. And I changed a bit the title of my talk. So I hope I can summarize what was the work of these two students and the ideas that we believe are behind this talk. Okay, so this is one of the most important plots, the stellar to halo mass ratio as a function of the halo mass, and it's a cumulative plot that is telling us how efficient were the dark matter halos in converting gas into stars. So we see that there is a peak around 10 to the 12. Dark matter halos, Milky Way size halos have been the most efficient halos in transforming gas into stars. And we can see the important point of this plot. You can see that we can use different ways to obtain this relation. Most of them are doing very well at low redshift, depending on and it's independent of the technique. Now, we know that this correlation has some scatter. And here I'm showing some a bit old plot from my 2015 paper, but I think the state of the art is more or less the same. The scatter around the stellar to halo mass ratio, or the stellar to halo mass relation, is more or less constant. It's around between 0.15 dex or 0.2 dex, and it's less constant with halo mass. Now, let's introduce a question. So what causes that some galaxies stay above or below the stellar to halo mass relation? The fact that we have this scatter around this relation, now I'm showing the stellar mass versus the halo mass. The fact that we have this scatter around this relation for a given stellar mass, what causes that there are different galaxies? Well, there have been some works in which now, and this is very important, I'm plotting here the halo mass versus the stellar mass. There are some work based on weak lensings, satellite kinematics, or groups, where they show that for a fixed stellar mass, galaxies that are quiescent, red, or elliptical morphologies have larger halo mass than star-forming galaxies. And I'm talking only about central galaxies. So this tells us that some parameter behind this scatter should be the star formation rate or the color of the galaxy. Now, in check that I using now here in the x-axis, the halo mass, when we try to understand this from view of different types of modeling, we know that there is a contention among some authors. So here I'm plotting the difference between the halo mass of a quiescent galaxies and of a star-forming galaxies. And here you have different authors. So this is actually from Periodic 2019. So you can see that some authors predict that there is no difference between those models. And there are some authors that predict that star-forming galaxies will have larger, quiescent galaxies will have larger halo mass, and other authors that predict the inverse. Now, this plot is very important, and as I will show you later, the models that predict that halo masses have larger halo mass for a given halo mass, and those that are around that show that they are equal, the primary determining factor for the clustering will be assembly bias. Now, those that predict that are in this region, the main determining factor will be halo bias. So understanding from the point of view, theoretical or empirical, this plot, it's important to understand how much assembly bias is affecting galaxy halo connection. So what is assembly bias? Okay, so here we are comparing the bias versus the halo mass. This is normalized by this nonlinear mass, which is around 10 to the 16 solar masses. So this means that we are going from low mass halos to higher mass halos. Low mass halos, and the gray line here is showing that low mass halos are less clustered than high mass halos. Now I would like you to focus on the red and the blue points, which means all halos and young halos. For a fixed halo mass, all halos cluster more than young halos. And this is the assembly bias effect. Now, because we know that star-forming galaxies or quiescent galaxies cluster more, one would be tempted to assign a halo assembly bias to those models. So what we have we seen in previous models? So this is a result from Verity 2021, which was very inspiring for our work. So we are seeing different ways, and they are trying to measure the correlation function in the specific star formation rate versus the polar plane. In all these ways that in this paper the authors divided their samples as a function of the specific star formation rate, the important point is that they are seeing a monotonic trend between the clustering and the star formation rate in the direction that highly star-forming galaxies cluster less than more quiescent galaxies. They check and see that how those models, like for example, Universe Machine does and predicts about the clustering on this model. What they observe is that, and this is an important point related to this talk, they see that for a fixed, for a fixed solar mass, highly star-forming galaxies, central galaxies cluster less than quiescent galaxies. So again, and the signal compared to satellites is of the same order as the central galaxies. So this is a very strong sign for assembly bias. Now we believe that we need to revise this work, and I will show you other results that will support why we need to revise this work. And this is the first paper that I'm going to talk about. So this is our first approach. So here we are. I'm showing the specific star formation rate versus the solar mass. And as you see, we are dividing into different levels of the star formation rate. So we compute the main relation of the star formation main sequence. And we make a grid around this relation. So we have galaxies for a fixed solar mass that are highly star forming, and galaxies are in the green valley and that are quiescent. So we define these samples, and each for these samples, we measured the clustering of the galaxy. Unsurprisingly, so you are seeing here the 2-point correlation function. So for different solar masses, low mass galaxies, high mass galaxies, here we are collapsing the star forming main sequence into 2 bins. So you are seeing that highly star forming galaxies cluster less than quiescent galaxies. Now, what happens if we divide this into central and satellite galaxies? Now you can see here the contribution of the satellite galaxies becomes higher as you go down in the star formation rate plane. And note that central galaxies, it doesn't seem to depend too much on the clustering. So actually here, if I show you the clustering for only central galaxies, you can see that in all the panels, clustering is independent for central galaxies on the level of the star formation rate. In other words, to the distance of the star formation sequence. And we checked with different types of group finders, and from all of them, we are getting essentially the same answer. Now, you ask the question, can we understand the galaxy-halo connection by doing another type of statistics with the clustering? So what we did is to cross-correlate central galaxies with satellite galaxies in the following way. So we are taking galaxies from some of these bins that we define as a function to the distance of the star-forming main sequence. And let's, for example, take this sample. So we cross-correlate galaxies that are central here with all the satellites of the same bin. In this way, we can prove better the one halo term, which will tell us what is the halo mass of this galaxy. So you're seeing here again different solar masses and different levels of star formation rate. we have the star-forming main sequence, green valley, and quiescent galaxies. And you can see here that now the clustering is very different depending to the distance of the main sequence. And actually, we can see the enhancing of the one kiloturn, meaning that as we go to lower star formation rates, we have more clustering one kiloturn for quiescent galaxies. In other words, the quiescent galaxies live in more massive halos. Now we check what are the predictions from different types of models. So we are coming back again to the autocorrelation function of central galaxies. We are using two different types of models. Two models that are that has the information of assembly bias. We are showing by this symbol. Now the circles is the SDSS, and one that is correlated only with the halo mass. So it's interesting that you cannot distinguish in autocorrelation functions of central galaxies. You cannot distinguish between these three models. The three models are essentially predicting the same thing. Now, if we go to the cross correlations that I showed before, you can see that the models that predict assembly bias are in tension with the observations. But the model that predicts that the halo mass is the king of predicting the star formation rate is in better agreement with the observations compared to cross correlations. And now these are the predictions of the solar to halo mass relation. So in the top panels, I'm showing the results of the halo model, and the other two panels, the models with assembly bias. On the left, I'm plotting the solar mass versus halo mass. On the right, I'm plotting halo mass versus the solar mass. So you can see here that these models predict different solar to halo mass relation, consistent with what I was saying before. So for a fixed halo mass, assembly bias model predicts that quiescent galaxies will have larger solar mass. This is inverted in the halo model. Now, in this part, we can compare to some observations. You can see that the three models predict the same stellar to halo mass relation for quiescent galaxies, but not for star-forming galaxies. And this is perhaps related to the number of satellite galaxies. That the fact that we observed that the number of satellites as a function of the solar mass of the central galaxy, we compared to different levels of the star formation rate of the central galaxy. For a fixed solar mass, quiescent galaxies have more satellites than star-forming galaxies. Now, I will go to another topic, which is related to this one, and and I will ask the question: how does the specific star formation rate or the star formation rate depend on the structural properties of the galaxy's characteristic solar mass? So we know very well the size-mass relation. So we understand this relation from redshift 0 to higher redshift around 3. For a fixed solar mass, we know that the star-forming galaxies have larger radii compared to quiescent galaxies. But now, what is the real shape, the continuous shape between these two relations? So we have this paper by Goods, 2011, and he showed that for local galaxies, there is like a non-monotonic trend between these three quantities. So actually, it's a very complex shape and very hard to describe. Later, Brennan took this problem again and showed that when you plot delta specific the distance to the star-forming main sequence, and the y-axis you plot the median effective radius, there is a continuous distribution. I mean, for low star formation rate galaxies, you have smaller sizes. For highly star-forming galaxies, you have larger sizes. And they argued that the complex shape that Woodsville found in 2011 was there were some bad photometry in their galaxies. And we thought that it was again we need to revise these two plots, and I'm showing now the results from this paper. So we are taking a sample of SDSS galaxies, of a very local SDSS galaxies. What I'm showing here are different solar mass bins. I'm showing the half-life radius as a function to the distance of the main sequence. The red colors are showing the median of the scatter plots that as you can see in the back. And you can see again that there is this non-monotonic trend between size and mass. And we make sure that we were using good photometry for those galaxies, which seems to be to produce a very complicated relation. So one is, so we thought that if we want to study this relation, we should understand better what is the star formation rate and solar mass. So if you come back to the basics and try to understand the shape of this relation, you will see that for low mass galaxies below 10, around 10.2, sorry, 10.3, 10.4 log of ms star, the correlation between star formation rate and the solar mass is very strong. It goes to the 0.5. But above that mass, the star formation rate is constant with mass. So this means that there is these two regimes, and we are talking only about the star forming main sequence. There are these two regimes where you need to separate the galaxies. So if we change, just to make the long story short, if we take this plot and we ask, let's invert the axis. So instead of studying sizes as a function of delta main sequence, let's invert the axis. Now let's study delta main sequence as a function of this. So you can see here that a nice relation emerges between these two relations. So we are showing different solar masses. Notice that this is below 10.5, which is the strong correlation between star formation rate and mass. You can see that a very nice relation emerges between, for the star forming main sequence. Now, we color code by the CERSIC index. You can see here that redder colors are essentially on the top of the star forming main sequence. Bluer colors, more these morphologies, are on the bottom of the star forming. Now, it's important to note that galaxies that are on the top with earlier morphologies have the same structure as those galaxies that are quiescent. This suggests that this might be a sequence, that we are seeing a sequence, an evolutionary sequence in these plots. Galaxies might be evolving around this relation in some way, but the fact that they reach the tip of the top of the star forming main sequence and have a large earlier morphology, they will go down to this quiescent region. Now we are showing here some dashed lines which are not fit with the data, and we are comparing to the mean relations. And I won't have time to discuss this, but we can discuss later during the breaks if you want. So we are showing that these dashed lines are consistent with the Kenny-Schmidt law. Now it's the same figure, but I'm color coding by the color gradient. So now galaxies are on the top of the main sequence. Redder colors will mean blue centers, and bluer colors will mean redder centers. So these galaxies have earlier morphologies, bluer centers, and are consistent with the structure of quiescent galaxies. Here's some picture about what I was telling about. We believe that we are seeing here that galaxies are on the top of the main sequence are it's a quenching path for, and it's a quenching fast path for future quench galaxies. We have another quenching path and it's still there. Now, what happens if we plot the high mass galaxies? So we don't see any correlation anymore, but what we see is that most of the galaxies that are now in the star forming main sequence have earlier morphology, meaning that perhaps quenching is happening during the main sequence. And if we plot the color gradients, we see that that those galaxies have negative color gradients, and quiescent galaxies have pretty good. So this is some other work in progress, and the motivation for all this work was to improve some empirical models. So I will go very fast. So the idea is to produce individual stellar to halo mass relations by fitting halo merger trees and using all these empirical observations that we observe in these two other works, and fit them with that information to the model. So the idea will have a multivariate distribution that depends on halo properties and compared to some observables, and grabbing here, and produce the galaxy hello connection. So here are preliminary results about that. And here are some results about showing how is the stellar to hello mass relation for these new semi-empirical models. We are trying to reproduce this bimodality of the stellar to hello mass relation, the clustering of the galaxies, actually the cross correlations of the galaxies, and we are also mocking submillimetric bands. And I just put this plot because of the discussion of yesterday about the counts and submillimetric bands. The solid line shows our new model, and it seems to be consistent with submillimetric. And I will give you this.
Thank you. Questions? Yes.
Could you say a bit more about how you separate centrals from satellites? Because a criteria which is not conservative enough can make the assembly bias signal stronger, and one which is too conservative can wipe out real assembly bias signals.
Right. So we are using different types of group finders. So we are using the Yang et al. Catalog, Temple, and Rodriguez. So Yang used a halo-based group finder. Essentially, he's assuming that galaxies live in dark matter halos, and he's finding the groups. And the way that we are deciding that it's a central galaxy is that we take all the galaxies within the group, and we look which one is the most massive galaxy.
Somebody, yes.
Yeah, I have a pretty technical question here. So, how much time do you have to spend, like for example, in CPU hours? How much time do you have to spend to find a halo versus star forming and quiescent galaxy connection model to fit to all of your auto correlation and cross correlation data?
Right. So I'm doing something very tricky. So what I'm doing in this part, so essentially the question is how much time it takes to produce this kind of galaxies. So what I'm doing is I'm doing a very complicated scheme of fits to the merger trees. So essentially I have fits where I can produce any merger trees I think with some probability, and I can produce this model in a second. I can produce millions of galaxies. It doesn't require too much.
Sounds good. Maybe one more question while Ken sets up.
Hi, thanks for the talk. Could you say a little bit more about the physical picture around your two quenching pathways for low mass galaxies? What would explain these two paths?
Yeah, right. So we have this plot. So if you concentrate, for example, in this stellar mass bin, where you have a more diversity of points. So we are seeing that on the top of the main sequence, galaxies have high galaxies, right? And the Sersic indices, the structure of those galaxies are consistent with quiescent bands. You can see here that there is a strong difference between galaxies who are on the top of the star forming sequence or below. The same galaxies, and I will go and back so you can see the differences. So you can see that this is Sersic index, this is color gradient. The same galaxies that are on the top have fluorescence, meaning that most of the star formation is in the center. We believe that this is some kind of compaction event. We don't know how is it, but we believe that it's some kind of compaction event. If we go and back, you can see that there are consistent points. Now, having that in mind, what we are seeing is that these galaxies have high star formation rate in the center, which increases the Sersic index, and potentially leading to a decrease in the half-life, half-mass radius, and these galaxies will undergo a rapid quenching. So we are expecting that these galaxies from here to go there, the quiescent region, at a very fast rate. We expect that this will happen in hundreds of years. Well, those galaxies will move more slowly to this quiescent region. these galaxies are increasing their size because most of the star formations, they have negative X-radiance. Most of the star formation is occurring in the atmosphere. They are increasing their size. And we expect that you will find those galaxies migrating from here to there at higher masses, not at the masses that I was showing, because they are increasing their size and their mass.
Okay, let's thank Aldo one more time.